Welcome all. So today our topic is like role of energy storage and electric vehicles in the optimal operation of power systems. So here we are going to see, okay, I will show in the outline of presentation. So in this presentation, we are going to see, so first we are going to see like integration of renewable energy sources like wind and solar, how to integrate into the power system and what are the issues and how to handle those issues related to power system. So we are going to study all this related to the power systems. So and then we'll see what are the ancillary services and how they are important for the renewable energy or storage. And then we will see, so nowadays we are going to include various renewable energy sources into the system. So there should be some kind of market structures or model. So in which market or which structure, so we have to follow, and which market structure renewable energy sources can be integrated. So that we'll see. And also we are going to see like uncertainty modeling. So like how to model wind power, solar power, or the load uncertainty in the power system optimization. After studying these renewable energy sources, we are going to see modeling of battery storage and electric vehicles. So how to model batteries and electric vehicles in your optimal power flow problem. So, and then we'll see a sample problem like problem formulation. We are going to see some kind of simulation results and then conclusions. So this is a brief outline of our presentation today. Uh, so now all of you know, so next slide is going to be like why renewable energy is required. So this is a general slide, so everyone might have known so why we need this renewable energy. So here quickly, if you see, so there is a demand for electricity is increasing. So to get this demand, so we have to depend on renewable energy sources, and also the conventional sources are depleting. Like so, there is a availability problem, so we have to go towards renewable energy, and also conventional sources are like they are like environmentally not friendly, so we have to meet this demand like an equitable and sustainable manner. So to get to meet this demand in a sustainable manner, we have to go towards sustainability options like renewable energy sources or batteries or electric vehicles. So we have to go towards that, and we have to meet these efficiency. We have to meet this demand efficiently and economically. So to get economically, because wind power, solar power, so previously they are like more costly or expensive, but due to the technology advances and government subsidies, so they are becoming now economically friendlier and environmentally friendlier. So that's why we have to move towards renewable energy sources. But okay, so if you see renewable energy sources throughout the world is going towards the renewable energy sources. If you say Denmark, they are setting the target like they have to meet the total demand of Denmark by 50% by 2030. So similarly, like Germany also, they have get the target of 35% and UK by 30% by the end of this year. So these renewable energy sources mostly, so if we say renewable energy sources, mostly they are going to be wind power or solar PV. But the main problem with this is they are spatially distributed and inherently they are like intermittent and unpredictable. So that means uncertainty and variability. So if you see wind power is like more variable. So because people say wind percent is variable, wind power is variable almost 80%. So that means suppose suddenly there is a sunny weather, suddenly it changes to cloudy. So that means it changes 80% of the variability in case of solar power. Whereas wind power is more uncertain. So we have to see there are two different terms, the variability and uncertainty. So wind power, the variability is less, but uncertainty is very high. Whereas solar power, the variability is very high, uncertainty is little less compared to the wind power. So these and also the load demand. The load demand is uncertain. It's not a new concept. The load is uncertain from several years. So in this case, we are going to see load uncertainty, wind uncertainty, and also nowadays the electric vehicles. So electric vehicles also create some kind of uncertainty to the existing power system, because we don't know, the electric vehicles start one place and it goes to another place and it has to charge or discharge, so at different places. So the uncertainty is going to be increases due to these electric vehicles also. So all these we have to meet in a sustainable manner. So like electric vehicles and renewable energy sources, so there are many advantages. So you already know they are going to reduce emissions, loss, cost of supply, peak shaving, reliability, voltage profile, power quality. All these are going to be improved. But at the same time, they have many issues when we integrate into traditional power system. So in this work, we are going to see energy storage and like using the batteries or electric vehicles. So in this work, because uncertainty is going to be created due to wind power and solar power, and to handle those uncertainties, we have to use some kind of storage batteries and also electric vehicles. So this is basically to increase the penetration of renewable energy sources. If we don't have any flexibility to the conventional power system, we cannot integrate wind power and solar power into the system. So we need some kind of flexibility. How to get this flexibility? So this flexibility we are going to get by using some kind of suppose if you say conventional generator, suppose you say some thermal generator, some hydro generators. So we have to keep some kind of reserves. So that means you can say some kind of spinning reserve. You have to keep some kind of reserves. Or you have to use the batteries, storage batteries, or electric vehicles. So, but if you take a large power system, the batteries and electric vehicles, they are going to be considered, but their capacity is limited. So nowadays, we are working towards improving the capacity of the batteries and electric vehicles, but still they play a major role in like compensating this uncertainty due to wind power or the solar power. Similarly, to handle or to improve this flexibility, people are also using some kind of demand response, because some customers they can agree to reduce their demand, but when they agree, the customers we have to give some kind of incentives or some kind of payment to the customer, because if you don't give any incentives to the customers, so they cannot participate in the demand response programs. So to wind uncertainty and solar uncertainty, to make up or to handle these uncertainties, we have to use batteries, electric vehicles, or demand response. So these are the solutions, or the options. So if you see, the solution is like we have to do spatial diversity. So each source we have to put it in a different places. So that creates the spatial diversity. And flexible conventional generation. So that means we have to keep a flexible conventional generation like hydro generators or thermal generators with high ramp rate limits. A ramp up or ramp down limits are high. So then we can say it's a flexible conventional generation. So to handle these uncertainties, you need some flexible conventional generation, or you have to optimize like grid operations and control, and also you can handle the demand side management or energy storage. So these are going to be some kind of solutions to integrate high penetration of renewable energy sources. So this is like a theory. So in the concept wise, so this is how you have to handle the uncertainty, but the real problem comes when you do the implementation. So generally, the traditional power system optimization, let us say it is an optimal power flow. So this optimal power flow is going to be uh, like Optimal power flow is generally without using wind power or the solar power. So that means it is a conventional generators or conventional thermal generator mostly, or some people they also use some kind of hydro generators and do the optimization. So that we say generally optimal power flow. But when we integrate more amount of wind power, there should be some kind of market practice, because some markets, because when you integrate wind power into the system, it may create several problems like voltage problem or the stability problem or some kind of protection problems. So you cannot integrate wind power as you want into the existing grid, because it creates so many problems. So there should be some kind of market practice how to integrate wind power into the system or the solar power into the system. So there are going to be some kind of market practices. So generally, in the world, people use two kinds of market practices. The first one is market practice one is wind power is schedulable or dispatchable. So this means wind power can also be scheduled similar to thermal generators. That means there is no difference between thermal generator and the wind generator. This is not true. But this market practice considers that. So how to then wind power is uncertain, the solar power is uncertain, but how to think it is like similar to thermal generator. So for that, what you have to do, you have to keep flexible generation plan. That means you have to include reserve operational plan. So that means you have to keep the reserve, in such a way that whenever there is an uncertainty, the flexible generation can meet the demand. Suppose let us say tomorrow you have to meet 10 megawatts, 10 megawatt generation by wind generator. But suppose tomorrow the wind velocity is less, the wind power generation is less. Let us say it is generating only 8 megawatt. So the remaining 2 megawatt power, so you have to get from the conventional generator. So that is nothing but you have to keep amount of reserve in the operational plan. So this kind of practice is generally is used in the North America, because they have a lot of reserves. They have flexible generation. So in North America, so people are going to use this kind of market practice. So that means the wind generator can also participate in the market, and it is similar to thermal generator. But whereas in market practice too, so it is called wind power is not schedulable or not dispatchable. So this means you cannot schedule the thermal generator, you should not schedule the wind generator or the solar generator similar to thermal generator, because there is an uncertainty. So because we don't have a sufficient amount of reserve. So this kind of market practice is used, is nothing but this policy is observe all the wind power. So all the solar power, whatever the power, you have to observe. So this kind of thing is generally is done by Indian power system. So in India, whatever the wind power, the solar power, totally observed by the system operator, but it is not always the same. Suppose if the system operators see some kind of problem due to this wind or due to solar, suppose he thinks that there is some stability problem or some overloading problem, some line loading problem. So then he may disconnect the wind farm or solar farm. So without informing you, the system operator has a right to disconnect. So for that, in this case, it cannot be just participate in the market. The wind farm just participate in the market. You don't get any price. Like it cannot implement or it cannot affect locational marginal price. So it just go as a price taker. It cannot influence the market. So just wind farm or the solar farm just go as a price taker. So this kind of market practice is generally used in all developing countries. So because of availability of less availability of or no availability of spinning reserves. So whenever those who want to work with the renewable energy, or the batteries, or the electric vehicles, they have to consider their work is belongs to which type of market practice. So whether they are working for market practice 1 or whether they are working for market practice 2, so they have to first decide their works belongs to which kind of market practice. Then we'll see, this is for any market practice, you need some kind of reserve. So reserves are nothing but ancillary services. Ancillary services are nothing but some kind of flexible services so that you can maintain system reliability, system quality, and safety. So these are the some kind of extra services. Like suppose you let us say, so these are nothing but some kind of reactive power support. To increase the voltage level, you need some kind of reactive power. So this reactive power is nothing but is an ancillary services. So generally, ancillary services cost is about 10% of total generation and the transmission cost. So let us say, so when we pay electricity bill at our home, we think that it is a generation cost. Or our customer we are paying, but this cost related to generation cost, transmission cost, and also if this cost includes 10% is going to be ancillary services cost. So this is nothing but it may be some kind of reserve cost, it may be some kind of voltage support cost. So this is generally some kind of frequency regulation. So you also study some kind of frequency regulation. This frequency regulation also comes under the ancillary services. So generally, these are the different ancillary services. So ancillary services related to FERC. This is nothing but Federal Energy Regulatory Commission. So according to this, so there are 6 types of ancillary services. That is like reactive power support or frequency response, energy imbalance, if any imbalance, because when we add wind power or the solar power, due to their uncertainty, there is going to be energy imbalance. When you do the scheduling, there is going to be energy imbalance. To handle those energy imbalance, you need some kind of ancillary services. And based on the once you decide which kind of market practice you are working for, then again these ancillary services or energy market is also going to be done by different kind of market structures. So generally there are 3 kinds of market structures. So when you study power system deregulation or the restructured power system concept, because this is very important when you do optimization, like optimal power flow. So for that, you need to have like separate energy and ancillary services market. So people, everyone think that when you have the market, they think that it is an energy market, but it's not correct, because the power which we are getting to our house, it contains the real and the reactive power. So that is nothing but a complex power we are going to receive. So which includes the energy and ancillary services markets. So there is a separate energy and ancillary services market, and also you have energy and simultaneous ancillary services market. This means energy market is cleared separately, but still all ancillary services are going to be cleared simultaneously. This is the second type of market structure. And third one is so co-optimization. So this is nothing but all the energies and ancillary services, all the markets are cleared at a time. So this is going to be like more optimal solution, but it requires good programming and high computational complexity. The complexity is high in case of market structure 3. So let us see. So what is the 3 different kinds of market structures? So this is nothing but energy market, regulation market, and reserve market. The first one is nothing but energy market. The second and third, if you see the second one and third one, these are regulation and the reserve. These two markets are related to ancillary services because when we have wind power uncertainty, the load uncertainty, solar uncertainty, there is a problem of the regulation because you have to see uh, to handle those uncertainties, you need to have some kind of regulating power or reserve power. So this reserve power can be battery storage or electric vehicles. So this is a batteries and electric vehicles comes under the reserve markets. So in this market structure, this is called sequential or separate. Sequential means first what we do, we clear energy market, then we go to the regulation market, we clear this, then we go to the reserve market. This is a step-by-step process. So this doesn't need high complex optimization process, but the solution obtained here is not optimum because if solution is not optimum means we are paying the customers, we are paying the more money compared to what we supposed to pay. So this kind of market structure is a not efficient way. So this is called unbundled mechanism. So that means separator. So if you see basic definition of power system deregulation, it is nothing but generation, transmission, and the distribution all are in one under one umbrella. But due to this power system deregulation, they are separated into different markets. So energy market is different, transmission market is different, and the distribution market is different. So like that, it is divided. So why we went for the deregulation means it has several advantages. Similarly, this market structure is unbundled. So this market structure doesn't give a good results. So for that, to overcome those results, so the next market is still compared to market structure one, this is a good one, but still it's not efficient one because in this market structure, what we are doing, we are clearing the energy market first. So that means energy offer, taking energy offer from the generators. So this generator can be thermal generator, maybe wind generator, or the solar generator. So we take energy offer from the generators, we run the energy market, the output is going to be energy. This means each single generator, how much it should produce. Because suppose a generator is there, its capacity is 500 megawatt. So you cannot run it to full capacity because you have to optimize. Some generator maybe they're running at low capacity, some generator may be running at high capacity because it everything comes under the optimization. So the system operator has to optimize for the energy. This means the schedules each generator how much it should produce. So compared to the sequential one, this is the better because energy is cleared, but ancillary services like regulation and the reserve, these are cleared simultaneously. So that's why we call simultaneous ancillary services markets. So compared to the previous one, this gives a better results, but it misses the trade-offs between energy and ancillary services. It misses the trade-off because a single generator, because we see a thermal generator, we think that in our house we have real power, only the real power. It's not correct because we have real power and also the reactive power. But who will give the reactive power? The reactive power also comes from the same generator. The same generator, the same synchronous generator is going to give the real power and also the reactive power. So this market is a real power, but the ancillary services market is a reactive power. So that means same generator is participating in the real market and also reactive power market. So that means same generator participating in two different markets. So it cannot optimize fully. So that means it cannot produce the generator may lose some income. So to avoid that, we have to go for third market structure. So that is nothing but simultaneous or co-optimization. So in this case, what we are doing, we are optimizing energy and ancillary services together. So that means, so we have energy market and ancillary services market are cleared simultaneously. So due to, because each single generator is giving wind like real power and also the reactive power. So there is an inherent relationship between energy and ancillary services market. So this is a market structure. So it has all offers. The system operator takes the offer from for energy, reactive power, and also the reserve. He takes all the offers and he gives us schedules. So the single generator is participating in all the markets. So it gives the like it recognizes the trade-off. So because it recognizes the trade-off, because the single generator can decide how much I can give for the energy, how much I can give for the reactive power, how much I can give for the reserve, so that the generator profit can be increased, which inherently the customers also going to be benefited, because the ultimate aim of any like wind power or the solar or any power system component is to minimize the total cost, or cost of production cost we have to minimize, because if you minimize the production cost, at the end the customers are going to pay less. So the price per unit we are going to pay is going to be down, because all the power system, the main aim is to reduce the total cost. So by using this market structure, the most economical dispatch is going to be obtained, because all this we are going to get from only one source. So the most economical dispatch is going to be get from this optimization process. So now for doing the wind power or the solar power, first you have to decide. So the person who is doing the work, he has to decide the work belongs to which kind of market structure. So that means what kind of optimization he is doing, and this kind of optimization is implemented in practically which country is implementing, because when you do the market or any optimization, it should have some kind of real implementation. Suppose if you don't have any real real situation, so it's going to be implemented after 10 years, maybe 20 years. It's going to be like imaginary. So we don't guess, we don't have the proof which kind of market or which country is implementing this kind of market structure. So once you decide your work belongs to which kind of market, then we will go for wind power, the solar power, batteries, and electric vehicles. How to implement all of them into our existing power system? Because in our existing power system, we don't have wind power or the solar power or the batteries or electric vehicles. Suppose let us say 10 years before, we don't have all this. So that time the market is the optimization is considered only like thermal generators, where there is no uncertainty, there is no variability. So, but when we handle this wind power, the two main issues are variability and unpredictability. So, as I told, unpredictability is nothing but is an uncertainty. So, so to handle these uncertainty or variability, we have to see how the system operator is going to be implemented, what kind of approach system operator is going to be decided, so that this variability or uncertainty can be removed. Real, it's not, if you see practically, if you speak practically, we cannot remove the uncertainty, but we have to model this uncertainty such that based on this modeling, we can decide how to overcome these issues by using some kind of batteries, some kind of electric vehicles, or some kind of reserves. So for that, we have to model first wind energy system. to model the wind energy system. So as we know, the wind power output is basically depends on the wind velocity. So this is a most common and a simple way of calculating the wind power equation. I think those who are working in the power system and integrating wind and the solar power, this is the most common equation so people used to model the wind power output. So this is a simple model. This is a linear relationship. If you see here PR and V, this relationship is linear. For the sake of simplicity, I am explaining this, but some kind of researchers, they also considered instead of linear relationship, they are considering quadratic relationship or cubic relationship to model the wind power output. If you see some kind of research papers, you can easily get linear relationship or quadratic or cubic relationship. So anyone is almost you can get the results almost the same. Maybe the little difference in after the points. Like suppose let us say if you get some 8 megawatt from this model, maybe 8.1 or 8.05 by using quadratic or the cubic models. So for your research, you can consider so anyone. So you can use linear, cubic, or quadratic. There is no issue. So generally, this equation says that like wind velocity, less than cut in or more than cut out, the power output is going to be zero because we cannot operate the wind turbine if it is very high speed or very low speed. So when wind velocity, this is a V is wind velocity is between cut in and rated velocity, then the power is calculated by using this equation. Whereas if you say the wind velocity is rated velocity to cutout velocity, so then the power output is going to be its maximum. That is nothing but rated output. Because let us say the wind turbine has some rated capacity. We cannot say that every time the wind turbine is going to generate its maximum power. Capacity is high, capacity is different, but actual the power produced is different. So capacity like maximum. So when the wind velocity is between rated to wind cutout, it's a maximum. But in other like when the wind velocity is between this range is different. So based on the wind velocity, the power output is going to be calculated or it's going to be different. So this is how we have to model the for a particular wind speed, the power output is calculated using this equation. So once you know the power output, but you already studied or you already know the wind speed or wind power is not exactly so how much you are going to predict because there is an uncertainty. So to handle this uncertainty, so there are different ways to handle the uncertainty. So, but we have to, there are different models. So in this work, we are going to see how to handle this uncertainty by using probability distribution functions. So probability functions are generally, so we already studied in our mathematics classes. So probability is something like a random, so we have to give a mean solution or the standard deviation. Like by using the mean or the standard deviation, so we are going to give an approximate or more reliable wind power output. So to get this power output, so we have to handle this uncertainty of wind power or the solar power by using probability functions. So generally, to get wind power, we need to have wind velocity. So generally, the wind velocity is follows the viable probability density function. So in the literature, there are many probability functions. Let us say you have Rayleigh's function, viable function, log normal function, or beta distribution function. There are different distribution functions to model this, but most of the researchers proposed that viable distribution is a more closer, the output which you are going to get is more closer for the wind speed. So that means wind speed is more closely follows the viable distribution function. So this is a equation for the wind velocity for the viable distribution function. So this is output, and this last equation shows this is a uh, probability distribution function for the wind power. So here the probability distribution function you can model using this. Here if you see it, there are some factors like K and C. These are called some scale factor and the shape factor. So generally the scale factor and the shape factor we have to decide based on the location where the wind plant is located. So based on the wind plant location, we are going to determine, so what is the C, what is the value of C, and what is value of the K. It depends on the location of the wind farm or the wind turbine. So you already know the wind forecast is uncertain. So for that we handle using viable distribution function. But if you also see the load is also uncertain, but load uncertainty is not new because load uncertainty is there from the last several years. So when we determine electricity from that time onwards, we have the load uncertainty. But compared to wind and the solar, the load uncertainty is not very high. So, however, we have to handle this load uncertainty also. To handle this load uncertainty, we have to consider the normal distribution function because generally the load distribution follows the normal PDF. PDF is nothing but probability density function. So this equation shows how to model the load using normal distribution function. So here the mu's the L says this L. The L is nothing but the random load or uncertain load. At a particular hour, what is the load is uncertain. So that is uncertain is here. L is the uncertain load. But mu is the mean and sigma is the standard deviation. So for any distribution function, you will be having what is mu and what is the sigma. So based on that, the power output or load demand we are going to determine. So similarly, you already studied that wind solar is uncertain. Similarly, the solar is also uncertain because solar energy is also uncertain. So this solar energy is basically depends on the solar irradiation or solar insolation. So this solar insolation, but the amount of power output from the solar insolation, the solar plant or the solar cell depends on like solar irradiation and also temperature. So so the power output from the wind farm or the solar farm depends on the solar irradiation and also the temperature. What is the temperature? So this model, if the equation which you are seeing on the screen considers only solar irradiation. So this equation does not consider the temperature effect. So this equation there is no temperature effect, but there are several papers those who considered wind like solar irradiation and also the temperature. For the sake of simplicity, so this model, for the sake of simplicity and also the non-availability of the data, so we don't have exact temperature data. So to avoid temperature data, so as we don't have exact temperature data, so I didn't consider temperature in this work, but so we have considered the solar irradiation. In this equation, G is nothing but solar irradiation. So let us say solar irradiation from 0 to some RC. RC is nothing but some constant. So let us say solar irradiation is some 200 watt per meter square or 300. So let us fix RC is some level. So if the solar irradiation is between 0 to and RC, then power output is calculated by using this equation, where PSR is nothing but every solar cell there is a maximum of the rated power output. Suppose if it is more than RC, then you have to use this. This GSTD nothing but it is a standard solar irradiation. So generally it is a 1000. So most of the works people use it is a 1000. So 1000 as a solar irradiation. So based on this equation, we are going to get how much power we have or how much power we are going to generate from the solar PV plant. So this is depends on solar irradiation. This is G. But as you know, this G is uncertain. The solar irradiation G is uncertain. So we have to handle. So once G is uncertain, what will happen? The power output is also going to be uncertain. So we have to handle this uncertainty. So if you say this is a simple solar PV generator, including the battery also. So let us say this is a small PV generator, solar PV cell or solar generator. So in this, from this, we are going to get some kind of power, that is PPV, nothing but the amount of power is getting from the solar PV cell. Here, if you see some PU, this is nothing but some kind of spillage power. That means some loss, because all the power we cannot extract from the solar PV cell. Some power is going to be lost. So that loss is going to be PU. PU is nothing but some kind of spillage power. This is not high. It's a so this so we have to design such that this power is going to be less. So this power is we are going to give it to the controller and some kind of inverters. So this part includes some power electronics. Then we will be having some battery also. So this battery is not mandatory. So some PV units will have batteries, some PV units no. So this battery is basically to suppose is basically to charge or discharge. So when we have extra power, then you can take into the battery, or you have less, then you can discharge. So that's why it is a bidirectional. PB is a battery power is a bidirectional. So based on this, the PS. So this is like a standalone. But when we have a power system, we cannot say it is a standalone system or isolated. So it's not correct. Because when we have large power system, it's always going to be connected system. Suppose you have only microgrid, a small capacity, then it can be isolated microgrid or non-isolated. But in a regular power system, whatever the power you are generated from the wind, the solar, the battery, finally it is given to the power grid, power network. This is a bus. This bus is nothing but is a final network, big power system. So this is a power is given to the existing grid. So this picture shows a battery storage along with a solar energy system. So there is an uncertainty of this solar energy also. So to handle this uncertainty, because we don't have exact solar irradiation, we don't have G, we cannot predict exact G, because there are some good forecasting techniques. So you can say there are many research papers on forecasting, wind forecast or solar irradiation forecast. There are many forecasting techniques. So by using those forecasting techniques, we are going to get the exact forecast. But still, if you say any forecasting technique is not 100% accurate, there is going to be some error. That MAPE. If you are in forecasting side research, you can find there is a actual power and forecasted power. Always there is going to be small mismatch. That is an error. So as we know, the solar irradiation is not exactly is a not we don't know like how much amount is going to get exactly after 1 day or after 1 hour, we don't know. So there is going to be some kind of uncertainty. So to handle those uncertainty, So we are going to use some bimodal distribution function. So this bimodal distribution function nothing but we will have two unimodal distribution function. Whereas wind side it is only unimodal function, but whereas solar is a bimodal distribution function. That means you will have you will have two functions like this. If you see here, there is omega and some equation and 1 minus omega and another equation. Because here we are going to use 2 because it is a unimodal function. So generally, these functions are handled by using beta distribution function, viable function, or log normal. So most of the researchers they used beta or viable. Log normal, not many people used because it deviates from the actual wind or the actual solar irradiation. So most of the research papers which you look into, so they handled this solar uncertainty by using beta function or viable function. So this is the equation for the viable function. So in this work, I used viable function for the wind and viable function for the solar. But some people they already used beta distribution function. So for your research, you can decide and use beta or normal. Both almost give accurate or the same result. So now you modeled, by this time you know how to model the wind power and the solar power. Now let us see how to model battery energy storage in a regular power system. So we have to model battery in our power system because power system it doesn't know what is charge, what is discharge, but finally we have to give for the power system you need only how much power you are giving or taking. That means you are charging or discharging. The power system, the actual power system, it knows only the power. So how much power is charging or discharging to the grid or from the grid. So so we have to decide how much power is giving or taking. So for the charge or discharge, the battery, so charge equation, the battery, this is charge or the discharge equation to the battery. Because every battery, there is a capacity of battery charging or the discharging, or how much it has the maximum capacity to charge, how much is the maximum capacity for the discharge. So this is the when you purchase or when you design a battery, so that information will be available. So for the power system, we are not concentrating on the design of the battery, but it's not exactly the design of the battery, but for the power system, what we are doing, modeling of the battery to use in our power system. So so for this, every battery will have maximum charging and the discharging capacity, and this batteries place the state of charge. Every battery, so even for the electric vehicles, you have the battery, and every battery you will have state of charge. So every battery state of charge is depends or controlled by using its maximum and the minimum capacity. So here T means time because when you suppose you have an electric vehicle, suppose you are driving electric vehicle for the 2 hours or the 3 hours, the state of charge every hour is different. If you do optimization for the 1 hour, suppose you are doing optimization for the every 30 minutes, so then you have to calculate the state of charge of your vehicle, of your battery's vehicle. So you have to decide or you have to calculate what is your state of charge at a particular time. So to find the state of charge, you need to have what is the charge of the battery and what is the maximum charge. So if you know these two levels, then you can determine what is your state of charge. So this battery charge is a B is nothing but battery energy storage. The charge of battery energy storage is generally you decide or you calculate by using this equation. That is nothing but by using charging power and discharging power and charging efficiency and discharging efficiency. Because every battery, it depends on efficiency, like charging and the discharging. So this is how you have to model your battery into your existing power system. See, whatever the study we are doing here is a large capacity, and also you can also consider for a small capacity if you are doing for the microgrid. If it is a if you are doing for the normal power system, it's going to be very high capacity in terms of like megawatts. And you can also model the electric vehicles. So in our power system, the electric vehicles are going to be modeled similar to the battery modeling, almost the same. But the thing is, the existing battery are standalone batteries. So if you say battery energy storage system, nothing but they are going to be standalone. The standalone batteries, the uncertainty is very less or negligible. Whereas the electric vehicles, because electric vehicles are used for the driving, so they are the dynamic. So when you use the batteries of electric vehicles, there is an uncertainty because we don't know so when we are going to charge, when we are going to discharge. So if you have some urgent work, you are going to drive, so that means there is an uncertainty. So when you do the electric vehicles, you have there is a some kind of uncertainty because electric vehicles also play two roles. So they can appear as a load or they can supply the demand. So when you have batteries, spare energy they can supply. So so electric vehicles can also play two roles. They can act like a generators, they can act like a loads. So for instantaneous charging status, so at a particular time, the instantaneous means at a particular time, the amount of power of electric vehicle is calculated by using this equation. So it depends on P is a zero means it is a starting. Suppose you are driving now, what is the initial power? So that will be here because this is required. It is nothing but in control system. Let us say it is an initial condition. So for an electric vehicle also, when you start the vehicle, what is your initial power or initial state of charge? In the next hour, whether you are charging or whether you are discharging. So it depends on. So next hour, suppose next hour you don't have any work, you are going to charge. Or let us say next hour you have you have to go to your office, so you have to drive for 1 hour. So then it depends on the time. So how much time you are for charging or how much time you are discharging, and it depends on your battery capacity. So as I already told, so every electric vehicle there is going to be some kind of uncertainty because we don't know when it's going to be charged, when it is going to be discharged. So to handle this uncertainty, we are also again using the distribution function. Like wind power and the solar power, we use the distribution function. Similarly, here also we are using distribution function which contains a mu is a mean, sigma is a standard deviation. Because every distribution function mostly follows some kind of curve that is nothing but distribution. Then in electric vehicles, it generally follows a normal distribution function. So in normal distribution function, so we have 0 to 12. That means if you divide the day into 24 hours, so 0 to 12 hours and 12 to 24 hours. So this is a distribution function used to model the electric vehicles. So now we've modeled how to model wind power, solar power, batteries, electric vehicles in our existing power system. Now let us say once you model, then you have to include or you have to integrate this into your existing power system. So let us say uh, demand side management. So this is, as I already told, this is suppose you don't have sufficient amount of capacity. Suppose you don't have sufficient amount of storage, then you have to use demand side management. So this is nothing but when you include the customers, when you don't have sufficient energy, then you ask some customers so that they can participate in the demand side management. So uh, so that is also one model to handle the uncertainty. So now let us see optimal power flow. I think this slide is everyone know about this slide. I think because it is a traditional or the regular optimal power flow problem. Because traditional optimal power flow, you don't have any wind power or the solar power. So you have only the thermal generators or hydro generators. There is no uncertainty. When we study our graduation or undergraduation level, we already studied like load flows or optimal power flow, because inside every optimal power flow program, inside every optimal power flow, you will be having load flows like Newton Raphson, fast decouple. So inside every optimal power flow, you will be having the load flow. So because let us say you have economic dispatch problem, economic dispatch. So the objective is to minimize the cost or to minimize the loss. Similarly, in optimal power flow also, the objective can be optimal load dispatch or minimum transmission loss. So this slide shows problem formulation of optimal power flow. So I'm saying in this, there is no novelty of this slide in this slide. This slide shows how a traditional power system runs. So a traditional power system is mathematically minimize or maximize. So suppose if you say cost, it's going to minimize. But those who have an idea about power system deregulation, you also have social welfare maximization. So that time it's going to be maximized. Here J is nothing but objective function. This objective function can be many. Let us say cost minimization, loss minimization, social welfare maximization, or let us say system reliability. So everyone wants reliability should be high. Suppose let us say risk. When we introduce wind power, solar power, batteries, electric vehicles, what you are doing? You are creating risk to the existing power system. You are making existing power system to get risk. So you have to minimize the risk. How to minimize the risk? To minimize the risk, so you have to model the risk and you have to optimize. So this is going to be objective function. And G, H are going to be some kind of equality and inequality constraints. So this G is says nothing but equality constraint. H is nothing but inequality constraint. Okay. So this is a traditional power system. So X is nothing but control variables. So like state variable. So state variable is nothing but so voltage, every bus, what is the voltage and what is the angle. But if you say control variables, so voltages of generators, power of generators, transformer. If you have transformer, then transformer taps. Suppose you have shunt, like shunt capacitor, like to improve the voltage profile, we use a shunt. So if you have shunt, then shunt. So this is a traditional power system or power system optimal power flow. But this slide shows without any wind or the solar or thermal, batteries, electric vehicle. So this is a traditional power system or traditional optimal power flow. So here if you see equation 1, nothing but load flow equation. Equation 2, functional operating constraint. Operating constraint nothing but suppose every bus you have some voltage, so you cannot exceed voltage or you cannot go below the voltage. So that is nothing but inequality constraint. So that is handled by using this operating constraint. Now we'll solve a small problem. So this is nothing but without any wind or the solar power. So in this case, you have optimal power flow, nothing but you just simply minimize cost of thermal generators. But now when we see total operating cost, the total operating cost, it contains power from the grid. So suppose if you see a microgrid system, how much power you are taking from the grid? That is nothing but how much power you are taking from the thermal generators. And this is a wind power. What is the cost? How much power? So that means how much wind power is we are using in the system. How much solar power? This PV nothing but how much solar power. Battery. So how much battery power? Here we are minimizing the cost. So that means every component, wind, solar, battery, electric vehicle, DR is nothing but demand response. So every component will be having some kind of cost, because in power system our main objective is to minimize the cost. Whatever you do, whatever you implement, whatever you introduce, the main aim of any system operator is to minimize the cost, because as a customer I want to pay less money. So I want to pay less money. This is possible only if I minimize this total operating cost. So this is the objective function. Objective function is minimize. So these are different equality inequality constraints. I just mentioned their names. I didn't include mathematical model due to the time constraint and due to like different mathematical model and understanding. So I just wrote these are the equality constraint or inequality constraint you have to include in the system. They are called nodal power balance constraint, generator constraint, constraint and battery energy storage. Like this is nothing but state of charge. What is minimum? What is maximum? Battery power. What is maximum? What is minimum? Battery. What is the capacity? What is the highest capacity? So these are all the constraints related to the batteries. Demand limits, because every demand also will have some kind of limit, because if you have an idea about demand side power system deregulation, every demand is divided into two types. They are called elastic demand, inelastic demand. So elastic demand you have constraint, inelastic demand you have some constraint. So so you have to decide your demand is elastic or inelastic. And also you have demand side reserve constraint, because when you use demand side management, so suppose I am the customer, I cannot say I want to uh, put off power to my house completely. No, I say I can reduce my power to some 20% less or 30% less, but still my house I will be having power, but I am using only 70%. I am using only 80%. So that is a constraint. That constraint is demand side reserve constraint. And the transformer constraint, as you know, every transformer will be having the taps. Every tap will have the constraint. Similarly, security constraint. So this security constraint is nothing but, so every line, every transmission line will have maximum limit, because thermal limit, we cannot exceed the maximum limit. That is nothing but congestion. So we have to uh, follow the congestion limit or the maximum power limit. So once you know this objective function and your constraints, then you have to implement this in a test system. So in this case, I have considered a small microgrid. See, whatever I modeled here, wind power, solar, microgrid, or batteries, you can use it for a microgrid or you can use it for a main grid, that is main power grid. The modeling is going to be same, only the capacity is different. Modeling will be same. In macro grid, the capacity is generally in kilowatt, whereas in a big grid or the utility grid, main power grid, the capacity is going to be in megawatts. Only that is a difference. Otherwise, it's going to be the same. So let us say in this macro grid, we have wind energy generator, solar units, batteries, electric vehicles, and demand response. Let us say all these components we have in our microgrid. Then what will happen? I am considering 4 windmills with the capacity 750 kilowatt and 4 solar PV plants with capacity 250 kilowatt. And I am also considering 2 battery units with capacity 250 kilowatt each. And also I am considering 2 electric vehicle aggregators, because each electric vehicle capacity is very small. So aggregator nothing but, so some electric vehicle together we bid or we participate in the market. So that is nothing but aggregators. So same like a battery units, they are going to be aggregator. So let us say wind farm means it is not only one wind generator or only one wind turbine. Several wind turbines together we call it is a wind farm or wind generator. In our power system, we say wind generator. That means it's not a single wind turbine. It is a combination of several wind turbines together. So when to do this, we need some kind of data. So that data nothing but what is wind speed data, solar irradiation data for 24-hour period. So let us say we are doing optimization for 24 hours. Then this is our data 1 to 24 hours. This is a load demand, wind speed, and solar irradiation. Sometimes solar irradiation is zero because in the night time there is no sun and no solar irradiation, or so not solar insolation. So this is the data we used for this simulation. So there are different case studies. So in this case one, what we are doing is we are considering all output from the main grid. Means we are not considering any renewable energy sources. That means no wind, no solar, no battery, no electric vehicle. In case one. In case two, what I am considering is I am considering main power grid and also renewable energy source. That means wind, solar I am considering. In third case, what I am doing, I am considering wind, solar, and also batteries and electric vehicles together. In fourth one, we are saying power output from wind, solar, batteries, electric vehicles, and also demand response. That means I am a customer, I can participate in the market. I can participate in the microgrid operation. So these are the four case studies considered in this work. And these are the I'm not presenting full result in the here. I'm just presenting a full result. You can search in the research paper. So but here I'm just showing only the main result or main table. So in case one, we are considering power output from the only main power grid. That means no wind, all these cost components we don't have. So if you use this, in case one, we are getting the cost is this 590,000 cost. But when we go to the case two, what we are doing, we are using wind power, solar power, and also main electric grid. So when we do these three, when we have these three, we don't have electric vehicle and demand response in this case. The cost has become 415,000. That means there is a change or there is a minimization compared to case one. So that means cost is decreased almost 12%. It is very significant cost. significant reduction in the cost, because here the cost is 590,000, it dropped down to 515,000. That means 12.6% is reduced. So this is for case 2. In case 3, what I am doing, apart from case 2, I am also considering electric vehicle or electric vehicle aggregators. So when we consider electric vehicle aggregators, the cost further decreased to 400,000. That means it is decreased, the cost reduction is almost 15%. Now, lastly, when we go to the case 4, that means in case 4, we are also handling or we are also including demand response. Suppose I am the customer, I can participate in the market. So in that case, the cost has become 494,000. This means cost is decreased almost 16%. So in case 1, without any wind power, solar power, batteries, electric vehicles, but when we include all the components of the microgrid, then cost has become 16% less. That means there is a reduction in the cost almost 16%. So this is one kind of objective, and these are the forecasted wind power and the solar power. So this shows what is forecasted wind power and what is the actual wind power. Similarly, what is the forecasted solar power and what is the wind power for the case 2, for case study 2. So this is for one objective. Now let us say, let us go for the next. So that means these results we considered for the microgrid, a small microgrid capacity in kilowatt. But let us say the next this is just to give you some research ideas. So because the main objective of any faculty development program is to learn the basics and then you can get some kind of research ideas what you can do in your research further. So to that, what I'm doing is, what I'm presenting is, let us say another objective one, objective function one, let us say operating cost. So this operating cost contains battery, like electric thermal generators, PG means thermal generators, PW means wind, PS is solar, battery, electric vehicle, and this is called deviation, because when we do wind power and solar power, there is no guarantee same power will get or not. So there is going to be some deviation. Deviation means, suppose let us say you tomorrow you get 10 megawatt, but you are getting only 2 megawatt. That is nothing but deviation. So we have to get the deviation also, some kind of cost for that. So this is objective function one. Let us say these are the different components like thermal generator cost, wind cost, solar cost, and battery cost, electric vehicle cost, and deviation cost. These are the cost components I explained in detail. So, as I told you, when I introduce wind power into the system, we are going to have some kind of risk. So, we have to model the risk also. Let us say this is called objective function 2. So, as you know, cost we have to minimize always, but at the same time, when we introduce wind, solar, electric vehicle, there is a risk. So we have to minimize the risk also in our optimization. So to model the risk, this is a fuzzy function is used to model the risk. So this is a one kind of mathematical model to model the risk into the system. And some other people they also used another one. This is also the risk, because to model the risk you can use different problem formulations. So why I'm presenting this is to give you some kind of research ideas where you can do your research further or next level. So for that you can also do some kind of This is called CVR, conditional value at risk. So this problem formulation is used when we introduce wind power, solar power into the system. So this is a problem formulation for conditional value at risk. So to model this, you need to value at risk. This is VAR. So conditional value at risk, but this is VAR. So for this, you have to model VAR first, then you have to model this function. So this I am presenting to show you some next results or what you can do further. So this is how you have to formulate. So this slide, and this slide shows how to find or how to formulate this conditional value at risk minimization or optimization function. So here for this, you have to consider some beta. Beta is nothing but satisfactory. This is like what is your satisfaction level? So that our confidence level. What is your confidence? Because there is going to be some kind of uncertainty, so you need to have some confidence level. So similarly, this phi c, nothing but probability. So in this case, we are considering wind probability as phi w, solar phi s, charging probability of electric vehicle is phi e. So all these are electric vehicles, batteries, wind, like probability. So how to model this probability in your optimization problem? So how to solve this? So to solve, I told you here two objective function. So to solve two objective function, we need to go for some kind of evolutionary algorithms or some kind of meta-heuristic algorithms. For that, you have to use. So in this work, I am presenting only one approach, or that is called non-dominated sorting genetic algorithm, that is called NSGA2. But you can use many techniques. There are many techniques available in the system. There are many techniques available in the system. So you can use any of the algorithm. So I'm presenting here only NSGA2, but you have many like multi-objective particle sum optimization, multi-objective differential evolution. There are many techniques in the literature. So you can select one and you can apply for your problem. So now I'm considering here uh, a big power system with cost is one objective, second objective is CVR, risk level is another objective, and third one is optimizing the cost and the risk both simultaneously. So three case studies I'm presenting. I'm not presenting you the full result. So as I told you, due to the time constraint, I'm presenting only the final table. So where you have three different case studies. In case study one, you have cost is objective. So that's why cost is minimum, but risk is very high. So whereas in case two, the cost is low, the cost is increased compared to this, cost is increased, but risk level is decreased. But in case three, what we are doing, multi-objective optimization. That means cost and the risk optimized simultaneously. So in that case, how to optimize? You have to use some multi-objective optimization algorithm. So then the results presented are best compromised solution. Okay, I will show you the best compromised solution. So this result shows total cost and the risk, and this result is the best compromised solution, or that is nothing but this point gives not very high risk, not very low cost. It is an optimum solution when you want to minimize both objectives. So this shows different voltage levels for case 1, case 2, and case 3. As you know, obviously, for case 1, the voltage is less. Voltage levels are going to be down because we are doing cost minimization. Whenever you do the cost minimization, the voltage is going to be down. So when you do the risk minimization, so the risk is minimized. So voltage profile is going to be improved. This, the second one, is going to be voltage profile in case of second. But third one, the voltage is in between these two because it is a compromise solution. So now I will present conclusions for this work. So in this work, we presented an optimization model for presenting the wind power, solar power, and then modeling batteries, electric vehicles, and then modeling into your existing power system, and then considering different objectives and how to model them in your power system. So for doing this work, these are the different, some of the reference papers considered for this work. And thank you. By this, I conclude my presentation.